lined up today. And the first theorem basically says something we all know. If you drive down the road, if you first turn right and then you turn left, the result is the same as if you first turn left and then right. Wait, is that true? No, that's not really true. Well, anyways, so it says something along those lines. I'll get to it. And the other one says basically, you remember this function? The function was x, y divided by x squared plus y squared. So in polar coordinates, it was sine theta. So it's constant on radial lines, but the constant is different depending on which radial direction you take. So this is an example that has partial derivatives at 0. The x derivative is 0, the y derivative is 0, but the function is not even continuous, right? So our second theorem, and one of the main theorems of this course, says that this kind of situation is very exceptional. So if the partial derivatives do exist and something a little bit extra, then things are fine. Then we cannot have situations like this that we have discontinuities at the same time, differentiability. So, but let's get through some definitions and then we get to these exciting theorems. So, and then Control L. And you go. So, higher order partial derivatives. So we have already discussed what's a partial derivative, right? So you can differentiate with respect to x or with respect to y if you're in two variables, x and y. And put the camera here so you can see me. And okay, so this we covered already. Here's the definition. Anyways, so for the x derivative, you just take a normal derivative with y variable frozen and x as the variable, right? So here's the definition: a plus h minus f of a comma b. So the comma b is the same, and then you divide by h, take a limit. Right, so f is called partially differentiable at the point if both the x and the y derivative exists there. Now, this gives rise to new functions, right? So, So let's work with an example here. You see me now? Okay. Right, x to the power of 3, y to the power of 4. Then df dx is a new function of x and y, just obtained by differentiating the x variable, right? Oh. And likewise, the y derivative is a new function, but not the same. So there's nothing that can stop us from going on differentiating these two guys, right? And get new functions again. So then the only question is, what should we call them and what kind of role do they play when we analyze functions? Well, the latter question will be answered in due time, but what to call them, it's written here. So if we differentiate these again, we get the second order partial derivatives. So differentiating the x partial derivative with respect to x again has this notation. So we put a square on the delta upstairs and a square on the delta x downstairs. I remember when I was a student, I thought this was strange because it looks like you're taking delta, differentiating with respect to x squared or something like that. That's not how it's supposed to be read. It's just, it's basically, you should think of it like this, that you take this is the operation you're doing, delta x. This is the symbol for a derivative. And if you want to make that into a square, you can either write this, but that's a bit cumbersome. So another more natural notation maybe is this. So this is just notation, right? Just pointing that out, that this is not delta x squared, but delta x 2 times, so to speak. Well, anyways, what it means is you do delta, you take a partial derivative with respect to x on what already was the partial derivative with respect to x. So here are 2 other notations for it. Put 2 bars up here, indicating that you have 2 derivatives, and then xx, indicating that both partial derivatives are with respect to x. Or similarly here, you can put a 1, 1, indicating that you're differentiating with respect to the first variable. So then derivative with respect to y would be f double prime bis, it is called, f bis, and then 2, 2, or y, y. All right, so let's put an f here and an f here. So now we're differentiating this function. Here in this example, what do we get? Well, we have 3x squared. So now we get 6x y to the power of 4. And then there are the mixed partials, okay? So that's doing, now I can differentiate df dx with respect to y as well, right? And notation-wise, it's a bit, this looks a bit long. So we cut it short. Again, we write a d square up there, or partial square. And down here, we just write dy dx. So it's implicit here in the notation that x comes before y. Not implicit, explicit. So that's how you read it. So anyways, what is this derivative? Now I differentiate this thing here with respect to y. So I get 12 x squared y to the power of 3. Of course, okay, then let's complete the list. So then I can also differentiate the y derivative with respect to x. And then my symbol for that comes like the previous one, but the roles or the order here is switched. And what do I get? So now we take this guy, 4x3, y3, and differentiate with respect to x. And this gives us 12x squared y to the power of 3. All right, so here we noticed something that is not a coincidence. And this is what I said, if you're on a road and first you turn left and then right, or turn right first and then left, you get the same thing. It just occurred to me that was false analogy. But still, if we differentiate with respect to x first and then y, or y first and then x, you get the same result. That's a theorem, and it's called the equality of mixed partials. And right, it's one of the important results of the course. So we're going to prove that in just a little while. Just to finish off here with our notation, we can do dby on df dy, giving us, well, notation-wise, it's shorter to write like that. But at the end of the day, yeah, we get 12 x3 y2. Yeah? So definitely no similarity here, and also there shouldn't be. So before we get to that theorem and its exciting proof, here's the example I just went through. And to continue, we could also go even higher, right? So now the second order derivatives, we have four in total, but two of them are the same. So in effect, there are three distinct ones. And all these three functions can then be differentiated further. So you can come up with things like this. So if we take this guy and differentiate it with respect to y, then we get the 4 goes down here. So you get 24x times y to the power of 3, which is what's written here. And all right, so this thing with the mixed partials, here you see another one, which is the same function, but down here in the denominator, it looks different. So here the order is dx squared dy, which means we have basically taken this one and differentiated this one with respect to x. So then we have 12 here. When we do the derivative with respect to x, the 2 drops down, so 12 times 2 is 24, and we get this thing again. So that also follows from the mixed partial derivatives theory. Okay, so terminology. Let omega be an open subset of Rn and f a function on omega. So we write f is in C of omega if f is continuous in omega. Now we add a 1 here to say that f is continuous and the first order partial derivatives exist and are continuous. Yeah. And this is the key issue that separates, you know, difficult functions from nice ones. So if we go back looking at this guy here, it has partial derivatives at all points, but they are not continuous functions. Yeah. So the partial derivatives exist everywhere, but as functions of the variables, they are not continuous. And that's when things can go wrong. If that does not happen, then you know, things are very good in the sense that we can use differential tools to analyze our function very well. We get a good understanding of it by doing things like, you know, multivariable versions of Taylor expansions and similar that we will come to later in the course. So this C1 concept is important. That's like the well-behaved functions. And this can be lifted to any order, right? So if you can compute 3 derivatives of any order, you know, x, y, x, 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 y, 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 however you want to order them. And these functions, which get many after a while, if these functions are all continuous, then you call it, you know, C3 if this is 3 times possible, or CK if you can do this process k times. Or finally C infinity if any partial derivative, no matter how high the order be, is continuous. Okay, so first theorem of today, a function is of class, if a function is of class C2 on omega, where omega is an open subset, then the mixed partials are the same. Before getting to the proof, yeah, let's then just see that this basically means that anytime you can flip the, well, in algebra language, the differentiation is commutative with respect to different variables. And this means that you can always flip the order between two, but this means also if you have a third order derivative like this one, so here you differentiate it with respect to x, then with respect to x, and then with y. Then the x and the y in the end, you can flip them. Now y sits in the middle. Then you can take the x in the beginning and y and flip them also. And now it sits in the front, right? So this means that you can always reorder how you want, how you take your partial derivatives, as long as the amount of derivatives with respect to x is the same as the amount of derivatives with respect to y in the different orderings. And this also holds in higher dimensions. So if there's a c direction, we're in R3, then it's true also. But okay. I'll open that slide in just a little while. So getting to the proof. Right, so if you drive down the road and first make a left and then a right, you end up here. If you drive down the road, first make, no, I flipped them, but if you first make a right and then a left, you go there. If you first make a left and then a right, you go here. So that wasn't the same. But what we all know about going around the block is that, okay, if you come here, if you first make a left and then make a right, that's the same as doing nothing and then making a left. So maybe if I come driving from here, now the analogy is correct, right? First you make right and then left, that's the same as first making left and then right. Anyways, so this is basically what's behind this result. So if this point here is A, comma B, and this point, so here's some coordinate system X and Y. Here we have A plus H, comma B. And here you have A, comma B plus K. And in this corner, A plus H, B plus K. So let's see how this square naturally comes into the game. So we're interested in the x at the point A, comma B, let's say. So this we know that it is approximately equal to f of A plus H, comma B, minus f of A, comma B, divided by H. Right? So the value here minus the value there, and then divided by H. So if we do some like this, you know, fishy math, we don't care. Well, like almost equal is the same as equal. So we just keep on computing as if this was an equality sign. Then you would have one of you should mute your mic because it's like, I don't know, sounds coming. Well, anyways. So what would this be? Well, with the same logic, I should take this expression, evaluate it at B plus K, minus evaluating it at B, and then divide by K, right? So this would be Well, dx at a comma b plus k minus dx at a comma, no. Yes. Right. Yeah. So this is what we have. Just with the same logic as before. So now I went here, b plus k, subtracted this, and divided by k. But now let's insert what we have here. Then with some, if you think about it a bit, you get a plus h and b plus k minus, all right, so I'll write off what we get here. We get f of a plus h comma b plus k minus f of a comma b plus k minus f of a plus comma b minus plus f of a comma b. And do you see that, or did I write outside of the blackboard now? Is it visible what I wrote?
Yeah, we can see it.
Okay, good. Right, divided by h and divided by k. So you see, when studying this object, we naturally get an expression which involves the value at this corner and this corner with a plus sign, and the value at this corner and this corner with a minus sign. And here we can kind of almost see intuitively why the theorem is true. Because in this expression over here, there is clear symmetry, right? There's no difference between the first and the second variable. This corner comes out plus, this corner plus, this one minus, this one minus. So if I had done this in the reverse order, starting with the y derivative here and then adding the x derivative here, it's plain to see that I will end up with the same expression. Yeah? So that's the intuition behind the mixed partials theory. The problem is that in mathematics, well, right, I mean, so intuition is good, but it's not a proof. So we have to turn this into a proof. So at the end of the day, what's the value of this discussion is that this object here is a natural thing to look at, and this shows up in the proof. So this is what is called Q of H comma K, just the numerator there. Now, usually, when dealing with differences like this, we invoke the mean value theorem. Do you remember the mean value theorem, what it says? So mean value theorem says that there exists a point h, no, let's call it psi, such that 0 less than psi less than h, and f of a plus h minus f of a is equal to f prime of a time, sorry, f prime of a plus psi times h. Yeah, this was it's a kind of natural statement, right? If you have a one variable function, here's the point A, here's your point A plus H. And then, if you take the line between these points, so the slope here is given by this, A plus F in the right point minus F in the left point, and then you divide by H, you get the slope. And that slope, of course you get it, or just not of course, but if you look at this graph, there should be some point between A and A plus H where the derivative of the graph is exactly that. And that point, we call it A plus psi. Right? This was the mean value theory. Now, our problem here, so, okay, we want to use the mean value theorem on this expression, right? But here I have a one variable function, here I have a two variable function. But that's okay, right? We can add this comma b and still use the mean value theorem, right? So then this, I just add a comma b here times h. And then here, this is the first partial derivative. So it's a partial derivative with respect to x. So then it looks like this. But now, and here's the key thing to understand. This second variable b, for every different b, I have a different function here in the first variable, right? If I'm standing here and looking in the x direction, it's not the same function as if I'm standing up here and looking in the x direction, right? So, if we want to use a one variable result like this in a two variable setting, we have to understand that this psi actually also depends on b. So on different levels here, we get different psi's. And this is a complicating factor. This is why this proof looks a bit weird first time you see it. If it wasn't for this, let me just show you quickly how a fake proof would go so you get the idea. So, a false argument. So you do df dx is equal to, so let me skip the false argument. I think I will confuse you more than I will actually help in understanding the proof. Right, so what we're going to do to get around this problem is we're going to introduce new functions. U of x, which is equal to f of x comma b plus k minus f of x comma b. And then v of y is equal to f of a plus h comma y minus f of a comma y. Now with these two guys, we see that this function QHK, which we have up here, can be written either as UA plus H minus U of A, right? Because if I insert here A plus H, I get the first term here. Then minus, here's an A plus H, I get this term here, right? And then if I do minus U of A, then I do minus again. Here's the first term of U of A, and here's the second term of U of A, right? This guy with an A, and this guy with an A. So if you look at this, you see that it's easy to see that it's the same thing as this. But here's a clear symmetry again between the first and second variable. So with exactly the same philosophy, we see that Q can be written in this way. Now, the nice thing here is that U of X and V of Y are really one variable functions, right? So we can use the mean value theorem on them. And, you know, if I do my mean value theorem of U of X, it will give me one value psi between A and A plus, between 0 and H. Right? It will give me one value, which is valid both for the B plus K and the comma B here, because they both appear in this definition of U, right? So I do not get this problem I have up here, that my psi depends on where I am, if I'm on the upper line or the lower line. So that's the nice idea with introducing these two guys. So let me see, how much of the blackboard do you see? Okay. Yeah. Oh, that went way too high. It's hard to get the right height here of doing this. Maybe something like that. Right, so you still see the expression of Q. I see there are chat things written here. I usually don't. Okay, you're just talking nonsense with each other. Xi, yeah, I don't know. I have nothing against Xi. It's easy to write, you know. It's like if you cough or sneeze and you try to write something, then out comes Xi. But anyway, so where are we with this proof here? So there is this guy Q of H and K, which if we divide with H and K, is somehow equal to our mixed partial derivative. Now we have managed to express this Q in terms of a difference here of two one variable functions, and we're going to play around with these two and the mean value theorem to see that, to get what we want. Okay, so The mean value theorem says, if I apply it to the function u, so then q of h comma k is equal to u of a plus h minus u of a, which is equal to u prime of a plus psi comma h. And now, of course, it turns out I made a pedagogical mistake, but let me fix it rather than live with it. So always, when you write up the mean value theorem, you can always, either you pick your psi to be in between 0 and h, and then you write a plus psi, right? Or you just write psi, but then psi is no longer between 0 and h, but in that case, psi is between a and a plus h. It's a matter of taste, which one you go for. But picking psi like this has the advantage that your expressions get shorter. So let's stick with that then. So now psi is a number near a, not near 0. Okay. And what is this? So if we look at our definition of u, differentiating u just means differentiating f, the first variable at this point minus the same at the second point, b. So this says that what we have here is actually f prime x evaluated at psi comma b plus k minus f prime x evaluated at psi comma b times h. Right? And now here's the beautiful step. Here is where we would have stumbled if I had gone through the business of making like the false attempt on the proof. So if we look at what we have now, in the first variable there is a psi, and in both terms there's the same psi, right? So if I would have just used my mean value theorem on the q directly, or on this expression directly, right? I will get one psi up here, one psi down here, which are not necessarily the same. And by the time I hit this point, I have psi 1 and psi 2, and then I cannot do much with this. Now the psi is the same. This is thanks to introducing this function u. And then the only thing which is different is the second variable. Here I have b plus k, and here I have b. But then I can use the mean value theorem again, right? This time I use mean value theorem on the function y maps to f, the first derivative, evaluated at psi, comma y. Now this is a one variable function, right? And I've assumed that my function has C2, it has two continuous partial derivatives of any combination. So this is a differentiable function, so I can use mean value theory. So then I can continue my computation here. Giving me now f double prime or bis x and then y right? So now I use the mean value theorem on this one. So now I get some number eta here, and I get times a k, and I already have from before times a h. Yes? Where now eta is a number between b and b plus k. And now we are more or less done, right? So you still see the expression, yeah. So if we take this expression q of h and k and divide it with h times k, is equal to, well, this number here times k times h, but since I divide that out, I just get the mixed partial at some point psi eta where psi is near A and eta is near B. And this is no surprise, right? Because here I had approximately equal to. So the second partial derivative was approximately equal to this quotient. What we have here is that the second partial derivative of the mixed partial is exactly equal to this. But instead I pay the price that the point is a bit different, right? So what we have here in terms of this original thing, map I draw, is that this point psi, eta sits somewhere inside of this box, yeah? And then instead of having approximate equality, I have equality. What do we want to do now? We want to take a limit as h and k goes to 0. What's going to happen when h and k goes to 0? Well, this rectangle is going to shrink, and since psi and eta are inside it, this is like the squeeze theorem. Psi and eta also has to approach A and B, right? So psi and eta depends on h and k. But as those goes to 0, psi and eta needs to go to A and B respectively. So what we have is, so since when h and k go to 0, we get that psi and eta converge or go to A comma B, we can now take a limit here. So limit h goes to 0, k goes to 0 of qhk divided by hk. That's the same as the second partial derivative psi. And now I write this out explicitly. So psi and eta depend on h and k, right? But, oh, no, I forgot. I always forget this. Here should write limit still, right? Limit h and k go to 0, should stick in there. So psi and eta, they go to A and B when this goes to 0. So the limit here is just equal to mixed partial derivative. Sorry, here should be a y, and there should be a y. Okay, so what did we gain here with this whole argument? Well, a lot, but it's not so easy to see maybe. I mean, at the end of the day, we expressed one of the two partial derivatives as a limit of something, right? And we never used this function v that showed up. But that's, I guess I have to move this one up a bit. Right. But that's the beauty of the argument. So Q, it doesn't see X or Y any difference, right? So Q, if we were to restart this whole argument, then we would get exactly the same, well, we would have the same Q. We could do this argument again with the function V instead. And at the end of the day, conclude exactly the same thing, but with the order of X and Y flipped here. And that's how we see that they are the same. So let me write here, repeating the whole argument with V instead gives that the limit h and k goes to 0, qhk divided by h times k is equal to the second partial derivative, but in the reverse order. Yeah, and now since I since I expressed this partial derivative and that partial derivative as the limit of the same thing, then they must be the same. So yeah, I find it's a beautiful argument. It requires a bit of you know, you have to sit down and mull it over and to understand it properly. If you're planning on doing the oral exam, this is a definite thing to come up on the exam. So it's one of the key theorems in the course. And time is 9:10. So what I will do is I'll go out. You can chit chat. You can hear each other if you talk, right?
Yeah, we can.
Right. So I'll just leave the room. You can have a discussion about if you want to have a course representative and who that person should be, and yeah, then you just let me know by email when well later on today. So I will continue lecturing at. Yeah, let's cut this a bit short because there are many, like 15 pages today. So we'll do a short break. I'll start 20 past, okay? By the way, maybe you people are shy, you don't know each other so much. So who was the last one who said something?
It was me, Casper.
Casper, okay, you're in charge of the discussion now.
Oh God.
All right, I'm leaving the room.
So Casper, how is your leading role going?
I'm just I have no idea. Very important transfer of power. I agree. So I guess, like, has anyone in this group ever been a course representative before, or anything? No, no one answers.
Casper, I vote you.
You vote me.
Yeah.
Oh,
It
God.
feels like you're very experienced after this like half a minute.
Exactly. No, I have no idea. But I'm too tired for this.
Well, let's just vote you in, and then you can fall asleep.
I guess I can be course representative if no one else wants to.
Great, thanks, Casper.
No worries.
Long live the new course representative.
Yeah. I love democracy.
Hello and welcome back. So there are 12 more messages on the chat, but I don't know if they are for me. Well, if anybody wants, well, should I read this? Well, I don't know. Okay, so here's something. Am I sure that there's an oral exam? We usually have an oral exam. For those who wants the VG. So if you don't want the VG, which is the pass with distinction, there is no need to take the oral exam. Anyways, let's leave these kind of questions for when tomorrow during lunch we can discuss these kind of things. And now would like to continue with the lecture. Right, so last time we lectured, it was this one, right? Weierstrass theorem, a function on a compact set attains its maximum and minimum. So all right, so this thing with the oral exam, last time I had this course, we had an oral exam. It's possible that they made changes to that. I'm not sure. I'll look it up before tomorrow, okay? So no need to panic. Anyways, about the course, what happened now with my lecture 6? Disappeared. Right, so we jumped one lecture, right? That was last Friday, we didn't do it. So now we're on lecture 6. And okay, we did the proof of theorem 1. Let me move the camera. So here's this. Here you have the details of what I did on the blackboard. So you can go through this calmly. Now, all right, so what do we want to do with these partial derivatives? I already kind of told you this when we introduced the partial derivatives, that you can also use them to create like the tangent plane. Yeah, so you have the x, the y direction. Here's a point A comma B. Up here is some sort of surface, the graph of a function. The value of the function at A point B is that. Then you can create like a linear plane that goes through that point. And we engineer this plane so that, you know, the geodesic, if you want, along the x and the y direction, the tangent at this point is in this plane, right? But then we have functions. So if you just look at this graph, it looks like this plane is actually close to the graph values everywhere. And that's what we want from a tangent approximation, right? But we don't know that yet. So far, we've just written up the definition of what is the tangent plane. Yeah, and that is, so the tangent plane, I used the notation from from the lecture note. So then it is L of x comma y is equal to the function value plus first derivative times x minus a. So the displacement from a in the x direction, you take the first partial derivative, and then you do the same with the second. So this is the tangent plane. It's just a definition. There's nothing that really tells us that this one is anywhere near our function. Yeah? So if we look at this example, which is hard to paint, but that I described many times. Yeah? This one is 0 here, 0 here. So 0 on the coordinate axis, but like if you follow, you know, a line like this, then the value is 1. Yeah? So the profile in some of our radial directions, it goes up, it goes down, it goes up, it goes down, and it does this. Yeah? So nevertheless, the tangent plane, if we define this function like this, and then we can define it, so if f of x comma y is equal to this for x and y not equal to 0, and 0 when x comma y is equal to 0, then what is the tangent plane really? Well, the first partial derivative is 0, the second partial derivative is 0, and the value is 0 at 0. So here we get at 0 the tangent plane is what? It's just the xy plane, right? Nothing happens. So the xy plane is nowhere near the function. For some values near 0, for others, yes. On the coordinate axis, this is a good approximation. Off the coordinate axis, this is not a good approximation. So what distinguishes this situation from this situation? It is this, what I said before, C1. In the right-hand side example, the derivatives, the partial derivatives exist, but they are not continuous. Yeah? So if we have continuous derivatives, things like this will not happen. Sorry, my phone was ringing. Okay, let me move the camera back. There's nothing really interesting written on the right side of the board, but still. And then a bit like that. So the tangent plane is, I didn't even finish. At 0, the tangent plane is 0 as a function of x and y. So this, just a function doing nothing. Okay, so to talk about these things, we need to go through a bit of notation again. So then I move back my camera, because this is a bit of a just transportation stretch. This little ortho and big ortho, I hope you have seen them before. They take a little while to get used to. But they're very convenient for handling error terms. So usually error terms, you know, if you're in a situation like this, you have an approximation, and then at every point, you know, there's a small difference, a gap. between the actual value and your approximation value. And usually error terms have expressions, like in integrals, you have this Lagrange remainder, in Taylor polynomials. But they have horrible expressions, so you don't want to write all of that out. And sometimes you don't even have an expression for it. But what we are interested in is some notion of size, right? So how fast does this go to 0 compared to how fast the other variables go to 0? And what you want then is that the error is always, small compared to, the key terms in whatever your approximation is. So this ordo is a way of keeping track of who's bigger than who. So we're going to write f, which is a function of h. So now we're just interested in a neighborhood of 0. So let's say that h is the perturbation. So here in this, we're interested at the point AB, but then, okay, so your h, vector h with the bar on top could be like h comma k in the previous situation of the previous proof. So we will make a local investigation around this point. So let's say that just this point is 0 for simplicity. Okay, so this function f is big ordo h as h goes to 0. If there is some function b, sorry, if there is all right, so yeah, this, anyways, if in a neighborhood of 0 there is a function c such that the left-hand side is bounded by c times the norm of h here, so the right-hand side. Yeah, so what does this mean? It means, well, so yeah, anytime you see something left-hand side is ordo and then something written here, it's not necessarily the norm. It just says that this one is bigger than this one in the sense that there exists a constant such that this holds, right? So if I were to write something like f equal to ordo h, so f of h, ordo h squared, that just means that modulus f of h is less than or equal to c times h squared in a neighborhood of the point. So for small values of h, we don't care what happens when h is big. Yeah, so in one variable, so f of x equals to big ordo modulus x. That would be the corresponding of what we have here on the lecture notes. So f of h, big ordo norm of h. It just means that you can take a slope c, so you can make some sort of cone here with slope c, such that your function values, they can be how erratic they want, but they have to stay inside of this cone. So if x goes to 0, this cone pushes things down to 0, and your function values stay inside of this cone. Now little ordo is saying a bit more, right? So in this situation here on the blackboard, okay. So saying that f of x is big ordo modulus x, that's the same as saying that f of x divided by x in norm is less than or equal to some constant c near 0. So if we divide, if we look at f of x divided by x, this can behave extremely bad. Oscillate up and down. It doesn't need to have a limit. But the only thing we know about it is that it is bounded. So there's an upper C and a minus C, so that this guy stays in this corridor. If we now write little ordo, then we assume in addition that actually this can also not happen. So this guy has to have a limit 0 when it goes to 0. So this is, the white guy is big ordo X and little ordo of X. If I'm to paint that, it's like he can behave how bad he wants, but when you get closer to the point, it can still keep on oscillating, but it has to, converge to 0 there. So this is giving more information. It's bounded and goes to 0. So little ordo is stronger than big ordo. So if you understand this in the one variable setting, the multivariable setting is exactly the same. It's just that you look in all directions at the same time, right? So instead of dividing by X, you divide with the norm of H, right? So now, what do we want from our tangent approximation in order to distinguish somehow between what happens in this picture when things are nice and in this picture when things are not nice? What we want is, we can't just say that, the difference between the graph value and the approximation values should go to 0 as X goes to 0, because that's obvious. I mean, even these terms go to 0 as X goes to A and Y goes to B, right? So any linear approximation, any tangent plane you put here, no matter how bad it is, will have the property that if you look at the tangent plane and the function f and just looks at what happens when you converge to A comma B, it will go to 0, right? So we need something more than this. We want to know how fast does it goes to 0. Okay. So with that definition, it says here, okay, so we say that f is differentiable. So this is an important concept. Differentiable is much more than just partial derivatives exist. F is differentiable if the difference between f and its tangent plane approximation is small ordo, right? So, yeah. This is probably a little bit easier to see. So how he wrote it there, he had X and Y and A and B. So it's a bit maybe hard to see what's going on because we're not dealing at near 0. So another way of expressing it, so f is differentiable if f is differentiable at point A comma B if f of A plus H comma B plus K is equal to f of A comma B plus f prime x at a comma b times h plus f prime y at a comma b k. Am I writing out of the blackboard yet? No. Okay, so here we have something that's not linear. Here we have a linear plane in h and k. And now h and k are near 0. So what's the difference between what's written here and the difference between here is like what you saw in this graph here. On the right-hand side, you're on the plane. On the left-hand side, you're on the graph. So we want to understand how big is the error here, how big is the difference. And then the error term should be ortho the norm of hk. Yeah? So in other terms, f of a plus h comma b plus k minus f of a comma b minus fx prime times h. Okay, no, okay. A comma b times h minus fy prime a comma b k. This is the left-hand side minus the right-hand side, except for the error term. And what do I want to know about this? I want to know that, okay, so that's what I said. This should be small, but saying it's small is not good enough because this difference here by itself between the first two, it goes to 0 as x and y, sorry, as h and k goes to 0. Both of these two terms, here we have just depends on h, and this depends on k. So it goes to 0 as h and k goes to 0. So everything here goes to 0. Saying that something goes to 0 isn't good enough to say that it's a good approximation. But now if we divide with the distance to 0, yeah, this is the norm of h and k. And we force this quotient. So now we have something small divided with something small. If this goes to 0 as h and k goes to 0, then this thing here is actually much smaller than the distance to 0, right? In a sense. So that's what we want from our plane. This is the linear approximation. We want it to be, right, so here's my point A comma B. Here's my, H comma K deviation. So I'm standing a bit away from, okay, so, well, this is the point 0 then in the HK plane, right? So I'm standing here at the point, and I want to know that the difference, the error in my approximation and the graph is small compared to the length, the distance to 0. Yeah? This is a strong condition on the function. And that is what it means to be differentiable. So when we have that, it is very good. We will see in just a little while how good that is. So, okay, but this seems like a difficult thing to verify, right? So if you look at the quotient I have there on the blackboard, how would you show that this goes to 0? Well, he actually has an example here. So it takes a function e to the x plus 2y and does it the hard way. So it goes through all the details and checks that the corresponding limit is 0 at some point 1, 0. And I encourage all of you to look at this example carefully. A real benefit with holding lectures like this, where I can flip between Blackboard and just looking at the lecture notes, is that I can spend much more time discussing interesting things and less time going through tedious details. So anyways, I will not go through this example. It works with the exponential function. At some point, it does a Taylor expansion of it. yada, yada, yada. And after a while, it comes to a conclusion that, okay, the linear approximation. Okay, so let's make this concrete anyway. So we start to look at this example. At the value 1, 0, the function value is 1, right? And the first derivative is this, the second derivative is this. So, which at 1, 0 is e and 2e. So the linear approximation is just this. So now he has a number times h, and another number times k. He needs to look at the difference of the actual function value, which is e to the power of something, minus this linear thing, and show, and then divide with this and show that it goes to 0. So that's what needs to be done. Of course, then to do it, you need to have some skills in mathematical limit proofs, basically. So I skipped those details because here's the second main theorem of today, which says that you don't need to check this. So all functions are differentiable at any point, given that they are C1 smooth, which I introduced in the beginning of the lecture. So what does this mean? It means that the partial derivatives exist and are continuous. If you have that, you get differentiability for free. So this is, by the time we had oral exams, at least in this course, this is a point I noticed that many students miss. They seem to kind of confuse what is being C1 and what is being differentiable, or even forgetting the definition of differentiability. So the definition of differentiability is important. It is this one. It is not the same technically as being C1, but you get this for free if you're C1. If your function is C1, it is differentiable. So this thing holds. That's what I'm going to prove now with the remaining time of the lecture. So the examples, I'll let you look at them yourselves. So another way to use this, well, if you know that something is differentiable, then you can always approximate function values. And you did this also in analysis 1. So it's the same in 2 variables, right? So if you have a function and you want to know the value at, okay, some point which are near to integer values where you can compute explicitly derivatives and the function value, then you can approximate, right? So in this case, all right, so f at 3, 0 is 9, and then you compute the derivatives and blah, blah, blah. You insert the, so here you are 0.5, you know, your little h is 0.05, your little k is minus 0.02, and you insert them in the linear approximation, and you get some number. Okay, so instead of 9, which is the function value, you get 8.76. Okay, so there are exercises along these lines, and but I'll let you read this also for yourselves. So what about this theorem now? Suppose that f is C1 smooth in an open set, then f is differentiable at each point of omega. So that means that all these functions we looked at in the previous examples were automatically differentiable. You don't need to check that because you just check that the partial derivatives exist and that those are continuous functions, which since the previous lectures, we know that, you know, almost all functions we get are continuous anyway, so it's not a difficult thing to satisfy. So the proof of this theorem is actually easier than the previous one, and it is it's one of the most, it relies on one of the most common tricks in mathematics. I'll get to it. Let's just write up what we have to work with first, okay? So, a bit somber in here, is it not? I'll turn on the lights as well. That looks better, right? So at the end of the day, differentiability at the point something, a comma b, it boils down to understanding the difference between a small perturbation and so the value in a perturbed point minus the value in a point, right? So these, if we can control these two, then we're in business, because at the end of the day, what we want is to deal with this long expression here, right? But these two are just the partial derivatives, and this is the linear terms, so they are easy. It starts out with this difference. F in the perturbed point minus F in the base point. So if we can control that guy, we're in good shape, right? So how do we do here? So we have partial derivatives to work with. They work only along, x and y direction. But here, again, I just have my point A comma B and my point A plus H comma B plus K. And it's a diagonal to get there, right? So in the previous proof, we kind of dealt with that by forming this square and going different ways. Here we don't need that. We just go like this. We could go the other way around as well, but it doesn't matter. We just need to pick one of them. So what's this point here? It is A plus H, comma. Sorry, it is. Which way do I want to go? Let me see that I do it the same way as they do it in the proof papers. Otherwise, it gets just messy. What the hell? Right. So we're not going to go that way. We're going to go the other way. We're going to go like this and then like this. So this is the point. Oh, I'm getting tired. Okay, so we're interested in the point A plus H, comma, B, right? And that's that guy. So then we go like this and then like this. Fine. So what I know from the first partial derivative is something about the difference of these 2 points. What I know from the other partial derivative is something about the difference of these 2 points. Problem is that neither of these differences are in here, right? Because this point, f evaluated in this point, is not part of my expression. How do I deal with that? Well, here is like one of the most standard tricks in mathematical proofs. You just, if you don't have the point you want, just add it and then subtract it. Can't see what's written on the right side. There's nothing written on the right side of the board. Well, anyways. So here we go. F of A plus H, comma, B plus K minus F of A plus H, comma, B plus F of A plus H, comma, B. And now I believe you that you can't see what's written on the right side of the board. But still you are. but very soon you won't. Let me move the camera. Right, and then there is the minus f of a comma b. So look at this. Here I now have the difference between these 2 points, and here I have the difference between these 2 points. And both of them, I know something about using partial derivatives. I just have to be a little bit careful here. So here the difference is in the second variable. So this is f prime of a plus h comma, so f prime with some derivative with respect to y, and then evaluated at some point eta times k, again using mean value theory, where now eta is between b and b plus k. So here I have still a plus h in the first one. So there's a bit of an asymmetry here, right? Again, here's the difference, which I can control using the first partial derivative. At now some point psi, but evaluated at b. So here a plus h, here just b. This has to do with that this line goes here and the other one goes, I mean, if you had gone this road instead, then the orders would have been flipped. Okay, so psi is now a number between a and a plus h, and then here's an h. Okay, but then armed with this, we can now go back to this whole ugly expression that we want to go to 0. Let's call this big thing something. Let me call it just r of h comma k. So I've given it some name, so I don't need to write it up again. But anyways, so what the expression I have on the other blackboard is this difference here. And look here, this one and this one looks very similar to what I just derived. First partial derivative, second partial derivative, times h and times k. The only difference is that they are evaluated at a bit different points. So if I write out my r h comma k, it will be f prime x at psi comma b minus f prime x at a comma b times h. Yeah, so this part comes from here, and the other part comes from the linear terms in this expression for r that just went up with the blackboard. Similarly, with the second variable, I get this guy, a plus h comma eta minus f prime y at a comma b times k. And all of this should then be divided with the length of h comma k, which I can put here. So I want to show that this expression goes to 0. But that is now very easy because h is smaller than the norm of h comma k. K is also smaller. So these guys are bounded by 1. Yeah, so they are very well controlled. When h and k goes to 0, these numbers are less than or equal to 1. Whereas what's in this parenthesis, here I have the first partial derivative evaluated at 2 points, which are very near. So when h and k goes to 0, this point converges to that point. Yeah? So this difference goes to 0. Why? Because that's what continuous functions do. So I have assumed, this is where the assumption comes in. I have assumed that f prime x is a continuous function, and then this difference goes to 0 with h and k. Same here, a plus h and eta. Eta goes to b, and a plus h goes to a when h and k goes to 0. So this difference goes to 0. Right. That was the end of today's lecture. I hope you enjoyed it. And otherwise, you're welcome to complain about it so tomorrow during lunch hour. I'm all ears. I would like to have actually feedback of what can be done better and how you feel about the whole thing. So please feel free to bring that up with me or come with questions about proof or what you want. So tomorrow during lunch, I'm here on Zoom. And yeah, that's it for today, folks. Over and out.